Part 1. The Invisible Wall. Dated June 28, 2026. Framework. Author Richard C.J. Young. The Cross-Sector Thermal Unification Thesis. Act 1. The Hidden Ceiling. There is a wall that no engineer has ever built, no legislature has ever passed, and no general has ever ordered. It has no mass, no color, and no name on any engineering diagram. Yet it is the single most expensive structure in the history of human civilization. It is the reason your phone gets warm in your hand and slows down. It is the reason the power company cannot simply push more electricity through the lines on the hottest day of the year. It is the reason the most powerful laser weapon ever built by the United States military cannot fire at full strength for more than a few seconds before it distorts into uselessness. It is the reason that clean hydrogen fuel, which humanity has known how to produce for over a century, still cannot compete economically with oil pulled from the ground. It is the reason that the solar panels on your roof generate less electricity on a hot afternoon than they do on a cool morning, even though the sun is stronger. This wall is heat. And we have been building our entire civilization inside its limits without ever naming it. In 1965, Gordon Moore, the co-founder of Intel, published his observation that the number of transistors on a microchip would double approximately every 2 years. For 60 years, that prediction held. Engineers made transistors smaller, faster, and cheaper with clockwork regularity. But in the early years of this century, something changed. Moore's law did not end because of physics. It did not end because we ran out of ways to make transistors smaller. It ended with remarkable precision at the exact moment that shrinking transistors further would generate more heat than we could remove from the chip. The ceiling was not electronic, it was thermal. Today, the largest data centers on Earth consume as much electricity as medium-sized cities. Of that enormous power draw, 40%, nearly half of all the electricity consumed, is spent not on computation. It is spent on cooling systems. It is spent on industrial chillers, massive air handlers, and liquid cooling loops, whose sole purpose is to remove the heat generated by the other 60%. We have built a civilization that spends nearly as much energy fighting the consequences of its own processes as it does performing those processes. The wall has a price tag. That price tag is measured in hundreds of billions of dollars per year. This documentary is the first attempt to name that wall precisely, to measure its cost across 5 separate industries simultaneously, and to describe the single manufacturing breakthrough announced not by a defense contractor or a technology giant, but by a university laboratory in Houston, Texas, in February of 2026, that has the potential to demolish it. Act 2. The grid that cannot carry its own load. The American power grid is the largest machine in human history. It spans 3 million miles of transmission and distribution lines, connects over 7,000 power plants, and serves 330 million people. It was built to carry electricity from where it is generated to where it is used. And it fails at this task every single day, not from sabotage, not from mechanical breakdown, but from heat. Every electrical conductor, every wire, every cable, every transformer winding has a property called resistance. Resistance is not a design flaw. It is a fundamental property of matter. When electrical current flows through a conductor, a fraction of that energy is converted into heat. The more current you push, the more heat is generated. This is the resistive heating effect, and it is inescapable under any conventional conductive material available today. Grid operators confront a specific consequence of this physics called thermal derating. On the hottest days of summer, when air conditioning demand peaks and electricity consumption surges to its annual maximum, grid operators are forced to artificially cap the amount of power flowing through their transmission lines. They do not cap it, because the lines are damaged. They cap it because allowing the lines to carry full load on a hot day would cause the cables to sag from thermal expansion, potentially contacting vegetation or infrastructure below, and would cause transformers to overheat and fail. The grid physically cannot deliver full power at the exact moment maximum power is needed. The thermal ceiling becomes a capacity ceiling at the worst possible time. The quantified cost of this constraint is not theoretical. The United States loses between 6 and 8% of all electricity generated to resistive heating in transmission. At current generation volumes, that is between $20 and $25 billion worth of energy evaporating as waste heat every year. The grid does not need a wholesale replacement to solve this problem. It does not need thousands of new transmission towers or a complete rewiring of the national infrastructure. What it needs is a thermal bypass at the choke points, at the transformer junctions, at the high voltage switching gear, at the nodes where heat accumulates and forces derating decisions. That bypass does not currently exist at commercial scale. The closest material capable of providing it has a thermal conductivity more than 5 times that of copper, is chemically inert, is electrically insulating when undoped, and until February of 2026, could not be grown on complex industrial components at any manufacturable scale. At Oak Ridge National Laboratory, engineers working under the Department of Energy's Advanced Materials and Manufacturing Technologies Office have been attempting to integrate CVD diamond heat spreaders into high-voltage grid inverters. The technology readiness level, as of mid-2026, is 4 on a 9-point scale. The engineering barrier is precise. When diamond is bonded to silicon carbide or gallium nitride switching components under heavy thermal cycling, the two materials expand at different rates. The mechanical shear stress at the boundary cracks the diamond's thermal pathway. Until that interface problem is solved, the grid bypass stays in the laboratory. The projected commercial crossing point, where diamond-assisted grid components become economically competitive with copper heat exchangers, is 2033 to 2035. That window is the target. Act 3. The hydrogen that cannot afford to be clean. In the summer of 2023, the International Energy Agency issued a report stating that green hydrogen, hydrogen produced by splitting water molecules using renewable electricity rather than burning natural gas, was the single most promising candidate for decarbonizing heavy industry. Steel manufacturing, cement production, long-haul shipping, and aviation fuel synthesis cannot run on batteries. They require a high-density, carbon-free fuel. Green hydrogen is chemically identical to hydrogen produced from fossil fuels. It produces 0 carbon when burned. It can be stored, transported, and used in existing industrial infrastructure with modest modification. The technology to produce it has existed since the 19th century. Green hydrogen costs between $5 and $6 per kilogram to produce. Hydrogen produced from natural gas costs between $1 and $2 per kilogram. That cost gap is the reason green hydrogen represents less than 1% of global hydrogen production, despite decades of policy support, subsidy programs, and stated industrial demand. The economics do not work. The primary driver of that cost gap is not the price of renewable electricity, although that matters. It is not the capital cost of the electrolysis equipment, although that matters too. The primary driver is electrode degradation. In a solid oxide electrolysis cell, the electrodes, typically made from nickel cermet composites, are exposed to extreme electrochemical conditions. High current densities, corrosive ionic environments, and thermal stress from uneven current distribution cause the electrode surfaces to degrade. Degradation shortens stack lifespans. Short stack lifespans mean frequent replacement. Frequent replacement means operating costs that cannot compete with the fossil alternative. Boron-doped diamond electrodes, grown via MPCVD on the ceramic substrates of electrolysis cells, are chemically inert to the corrosive conditions that destroy nickel kermet. They conduct electricity with extreme efficiency. They tolerate current densities that would destroy any conventional electrode material. The National Science Foundation and the Department of Energy's Hydrogen and Fuel Cell Technologies Office are both funding research in this domain. Element 6, a subsidiary of the De Beers Group and one of the two dominant synthetic diamond manufacturers on Earth, is among the industrial partners active in this development space. The technology readiness level, as of mid-2026, is 5. The engineering barrier is dopant homogeneity. Maintaining uniform boron distribution across the complex three-dimensional geometry of a porous ceramic electrode remains unsolved at production scale. The projected cost crossover year, where diamond electrode electrolysis cells produce green hydrogen at parity with natural gas reforming, is 2031 to 2033. If that crossing point is reached, the economics of the fuel from air scenario, synthesizing aviation fuel from atmospheric carbon dioxide and renewable electricity, shift from theoretical to industrial. The electrode is the missing component. The electrode is a diamond problem. Act 4. The sun that burns its own collector. The photovoltaic panel on a residential rooftop operates at a photon-to-electron conversion efficiency of between 20 and 22% under standard conditions. This means that for every unit of solar energy that strikes the panel, approximately 78 to 80% is not converted to electricity. Most of that unconverted energy becomes heat. The panel warms. As it warms, its conversion efficiency drops further. For every degree Celsius above the panel's optimal operating temperature, a silicon photovoltaic cell loses approximately 0.4% of its power output. On a hot afternoon, when a rooftop panel reaches 70 or 80 degrees Celsius above ambient temperature, it may be operating at 10 to 15% below its rated efficiency. The sun is simultaneously the source of the energy and the agent of the efficiency loss. Concentrated photovoltaic systems attempt to resolve this with optical multiplication. Rather than spreading a large panel across a large area, a CPV system uses a glass lens to focus sunlight from a large collection area onto a tiny, ultra-high efficiency, multi-junction solar cell, no larger than a thumbnail. The best multi-junction cells, made from stacked layers of gallium indium phosphide, gallium arsenide, and germanium, have demonstrated efficiencies exceeding 45% in laboratory conditions, more than twice the efficiency of standard silicon panels. These cells are extraordinarily expensive per unit area, which is why concentrating the light from a large lens onto a small cell is the only economically rational way to use them. The fatal constraint on concentrated photovoltaic systems is thermal. When sunlight is focused at 500 to 1,000 times concentration onto a cell the size of a thumbnail, the thermal load on that cell becomes extreme. Without active cooling, without liquid loops, without heat exchangers, without power-consuming pumps, the cell will reach its destruction threshold within seconds. The active cooling systems required to manage this heat are themselves expensive, failure-prone, and power-consuming. They reduce the net energy output of the system and increase its maintenance burden. Growing a CVD diamond backing layer directly onto the rear surface of a multi-junction CPV cell creates a passive thermal highway. No pumps, no fluid loops, no moving parts. The diamond conducts the destructive heat away from the cell junction at 5 times the rate of copper, passively, perpetually, with no degradation over the cell's operational lifetime. The National Renewable Energy Laboratory and research teams at Stanford University are pursuing this integration path under the Department of Energy's Solar Energy Technologies Office framework. The technology readiness level, as of mid-2026, is 4 to 5. The engineering barrier is yield. Growing a continuous, defect-free diamond layer across a full multi-inch semiconductor wafer without pinholes or grain boundary defects remains a manufacturing challenge at production scale. The projected cost crossover year, where diamond-backed CPV systems become competitive with silicon flat panels plus active cooling, is 2032 to 2034. The Rice University Selective Area Nucleation breakthrough, the ability to define exactly where diamond grows and at what grain density using laser-patterned seeding, is the most direct technical bridge between the laboratory demonstration and the production yield required to hit that crossing point. Act 5. The weapon that cannot hold its aim. In October of 2023, the United States Defense Advanced Research Projects Agency issued contracts under a program called LADIS, the Large Area Diamond Devices and Integrated Systems Initiative, to 6 vendors, including Element 6 of the De Beers Group. The objective was explicit: develop CVD diamond components for high-energy laser weapon systems at militarily relevant scale. In June of 2026, DARPA's Defense Sciences Office issued a new solicitation for high-duty cycle high-energy lasers with size, weight, and power constraints, specifically seeking innovations in thermal management of optical components. The Pentagon is not funding diamond optics research because the physics is academically interesting. It is funding it because the current optical materials used in high-energy laser weapon systems are failing at the exact power levels required to defeat modern drone swarms, cruise missiles, and hypersonic glide vehicles. A high-energy laser weapon operates on a straightforward principle: generate a coherent beam of light at high power. Direct that beam onto a target. Deliver enough energy per unit area to destroy the target's structural or electronic integrity. The economics of this kill chain, compared to a conventional interceptor missile, are transformative. A standard surface-to-air missile costs between $50,000 and $3 million per shot. A high-energy laser kill costs approximately $1 per shot in electricity. The asymmetric cost advantage of directed energy over kinetic interceptors is the foundational argument behind the affordable missile defense frameworks explored elsewhere in this documentary series. The technical barrier preventing high-energy lasers from achieving their theoretical performance ceiling is thermal lensing in the optical path. The output window of a high-energy laser, the final optical element through which the beam passes before entering the atmosphere, must be essentially transparent to the laser's wavelength while simultaneously tolerating the thermal load of absorbing a tiny fraction of the beam energy. In systems operating at 100 kilowatts or above, even a fractional absorption of 0.01% is sufficient to create a measurable temperature gradient across the optical element. That gradient distorts the refractive index of the material, a phenomenon called thermal lensing, which defocuses and decoheres the beam. The weapon's effective range and lethality drop precisely as the power increases. The material being replaced by diamond in this application is zinc selenide, the current standard for high-power laser optics. Zinc selenide has a thermal conductivity of approximately 18 watts per meter Kelvin. CVD diamond has a thermal conductivity of up to 2,200 watts per meter Kelvin. The thermal lensing problem essentially disappears at diamond's conductivity level. The technology readiness level for CVD diamond military laser optics is 6, the highest of any application in this documentary's survey. System prototype demonstrations in operational environments have occurred. Raytheon Technologies is among the defense primes executing MPCVD production runs for tactical laser exit apertures. The engineering barrier is optical purity. Sub-nanometer nitrogen impurities and microscopic structural voids in thick diamond windows cause absorption and scatter losses that must be driven to near zero. The projected commercial military deployment scale, where high-volume MPC-VD yields make diamond optics standard issue rather than experimental, is 2028 to 2029. That is the fastest crossover in this documentary's entire survey. Defense economics, unlike commercial economics, do not require cost parity with incumbents. They require performance parity, and diamond already delivers it. Act 6. The battery that outlives civilization. There is a category of infrastructure where the concept of replacing a battery is not a maintenance problem. It is a physical impossibility. Sensors embedded in the concrete foundations of major bridges, monitoring systems sealed inside the primary containment structures of nuclear power plants, communications equipment deployed in the Arctic, in deep ocean, in geosynchronous orbit, medical implants embedded in human tissue. In all of these applications, the energy source must operate without human intervention for decades. In the most demanding cases, for centuries. Nuclear reactors produce, as a byproduct of their operation, graphite moderator blocks contaminated with carbon-14, a radioactive isotope of carbon with a half-life of 5,730 years. Under current regulatory frameworks, this contaminated graphite is classified as low-level nuclear waste. Its management and storage represents a multi-decade liability for every nuclear operator on Earth. It will remain radioactive, by definition, for longer than recorded human civilization has existed. In 2016, researchers at the University of Bristol demonstrated that by heating carbon-14 graphite in a vacuum to drive off its contaminants, and then using that carbon as the feedstock for CVD diamond growth, they could encapsulate the radioactive isotope inside a synthetic diamond structure. The diamond absorbs the beta radiation emitted by the carbon-14 as it decays and converts it directly into a small, continuous electrical current. The result is a solid-state nuclear battery with no moving parts, no chemical reactions, no electrolyte degradation, no charging requirement, and an operational lifespan of thousands of years. The nuclear waste that was going to be stored as a liability for 5,730 years is instead grown into a power source that generates electricity for 5,730 years. The problem becomes the solution. The liability becomes the infrastructure. Deep tech companies, including Arconlight, a spin-out from the University of Bristol, and NDB Inc., are advancing this technology toward commercial field deployment. The technology readiness level, as of mid-2026, is 6. The engineering barrier is power density. The current output of carbon-14 diamond batteries is measured in microwatts, sufficient for low-power sensors and medical implants, but insufficient for the macro infrastructure power requirements that would make them transformative at grid scale. The structured three-dimensional PAN junction architecture that would improve charge collection efficiency from carbon-14 beta emission is the primary research frontier. The projected cost crossover for niche remote infrastructure applications is 2038 to 2040. The addressable market is not the residential power grid. It is every installation on Earth where the cost or physical impossibility of maintenance makes a multi-decade power source worth any premium. The funding oversight comes from the UK Atomic Energy Authority and the United States Department of Energy National Laboratories. The radioactive isotope that powers the battery is not mined. It is harvested from the waste stream of existing nuclear reactors. The input feedstock costs nothing. The operational lifespan is measured in millennia. Act 7. The unification. 5 industries, 5 thermal failure points, 5 cost ceilings holding back 5 sectors of industrial civilization, the power grid that derates on hot days, the electrolysis cell that degrades its own electrodes, the concentrated solar array that burns its own collector, the laser weapon that distorts its own beam, the battery that must last forever in places no human can reach. These are not 5 separate problems with 5 separate solutions. They are one problem expressed 5 times in 5 different industrial languages, using 5 different vocabularies developed by 5 separate communities of engineers who have never sat in the same room. The problem's heat. The thermal bottleneck is the universal constraint, and until February of 2026, there was no manufacturing process capable of addressing that constraint across all 5 domains simultaneously, because there was no manufacturable process for growing diamond. The only material with the thermal conductivity, the chemical inertness, the optical transparency, and the electrochemical stability required on the complex 3-dimensional surfaces of real industrial components. In 1856, Henry Bessemer did not invent steel. Steel had existed for centuries. What he invented was a way to force air through molten pig iron at scale, burning out the sulfur and phosphorus impurities that made iron brittle, converting it from an expensive, inconsistent material into a cheap, reliable structural product. The Bessemer converter did not improve steel's properties. It made steel's existing properties accessible at the price point and the production volume required for civilization-scale deployment. Every railroad, every bridge, every skyscraper built in the following century was built on the economic consequence of that manufacturing unlock. In February of 2026, a research team at Rice University's Wide Lab published a technique called selective area diamond growth via bottom-up nucleation engineering. They demonstrated that by using laser-defined seeding patterns to control where carbon atoms nucleate on a substrate surface and at what crystallographic density, they could grow patterned diamond layers on complex geometries with wafer-scale reproducibility for the first time. The technique did not improve diamond's thermal conductivity. Diamond's thermal conductivity is a fixed property of its atomic structure. What the technique changed was the cost and the geometric flexibility of deploying that property. Diamond's existing properties became accessible at the price point and the geometric flexibility required for industrial deployment. This is the Bessemer moment for carbon. The material did not change. The manufacturing did. The thermal bottleneck is not a law of physics. It is an engineering problem, and the engineering problem has a solution. That solution is being grown, atom by atom, in laboratories and eventually in factories, at the intersections of every major industrial system that heat has ever constrained. Part 2 of this documentary maps the deployment timeline, sector by sector, year by year, from the laboratory to the infrastructure. The ceiling is cracking. End of Part 1. Methodological Framework Statement, dated June 28, 2026. This documentary introduces the cross-sector thermal unification thesis, the argument that heat is the single universal constraint on industrial civilization, and that the Rice University MPCVD bottom-up nucleation breakthrough of February 2026 represents the first manufacturing unlock in history, capable of resolving thermal bottlenecks simultaneously across 5 unrelated industrial sectors: power grid infrastructure, green hydrogen electrolysis, concentrated photovoltaics, directed energy weapons, and long-duration remote power. As confirmed by comprehensive review of academic, industrial, and journalistic literature, as of June 28, 2026, no prior published framework has made this specific cross-sector thermal unification argument. Intellectual priority for this synthesized framework is claimed by Richard C.J. Young, documented June 28, 2026.